Hi Year 12, I thought I'd talk you through this particular worksheet, maximum flow, minimum cut. I'm going to go halfway and stop because it'll take too long, and then I'll do the other half. Okay, so pretty much all you have to do first of all is read through your textbook to work out all of the different SSTs. So I'll just read through that very quickly and we'll go through each of the SSTs. So the textbook, if you have it open, says a flow diagram is a weighted and directed network with a source vertex, so that's the start, and a sink vertex, that's the finish. So that's the difference with these particular flow diagrams. The source is also always labelled an S, and a sink is always labelled a T. Unlike an activity chart, a flow diagram represents a transportation network of objects moving from the source to the sink. The direction of the edges indicates the direction of the movement. Hopefully most of you know that already. If it's got an arrow, you know it goes in that way. And the weight of an edge represents the capacity or a maximum rate of movement along the edge. So there's a couple of your SSTs there. Okay, hopefully you've written those in as I was talking. Otherwise, I'll just leave it there. You can pause it if you need to write those down. Feel free to pause at any time. It says here the simplest example has only a source and a sink with one edge between them. That's in the textbook, one line pretty much, with the 1,000 on it. This network could represent two computers with a gigabyte Ethernet connection between them, where data can flow from computer S to computer T at a rate of up to 1,000 megabits per second. The network gives the capacities of each connection, but how much can actually flow from the source to the sink? Well, this is called the maximum flow or the flow capacity. So some other real-life applications of flow networks I've included here: the Ethernet connection, the flow of cars, even the flow of water down pipes. If you can think of another one, there's another thing there for you. Maybe we'll find one before the end of this activity. Maximum flow is the flow capacity that is as large as possible. Flow capacity is the total flow from the sink to the source. Now, some of these were a little bit confusing for me, but I watched some of those Bodgers movies and the Maths Online ones, and it did make a little bit more sense. So if you're reading through your textbook and there wasn't any videos connected to your textbook, I wasn't happy about that. Your textbook does seem to be a little bit confusing, so that's why I am trying to at least go through this. So if you're finding this confusing, I really suggest you watch the 10G, the Bodgers videos, because he actually goes through it in quite a lot of detail, and he made sense to me. He gabbled on a bit too long, but yeah, anyway. Two computers are connected by Ethernets. So basically in this particular diagram, you can only go as fast as your lowest number, okay? So it doesn't matter if it goes really fast to S to A. If you can only go 100 megabytes per second from A to T, then that's as fast as you can go, okay? So that's going to be your maximum flow in that particular case, and that's what they say there. Data can flow along the edge, S to A at a rate of 1,000 megabytes per second, but it will get slowed down at vertex A because no more than 100 megabytes per second can flow along the edge, AT. So the maximum flow from the S source to the T sink is 100 megabytes per second, okay? Gets a little bit harder when you get some other things in there. All right, so if you keep talking, it tells you about saturation. It says in this topic, an edge has two numbers associated with it: a capacity, given by the question, and a flow, which is to be determined. For each edge, the flow must be a number between 0 and the capacity. So in other words, you can't go over the capacity. If the pipe can only fit 1,000 litres down it, you can't go more than that, can you? So that's what that means. So we would say that an edge is saturated when the flow is equal to the capacity. So basically when it's the water flowing down it is as much as it can take. Okay, so that makes sense. Calculating the maximum flow in a network is a game. Move as much as you can from the source to the sink using as many edges as you like. The only rule is that there can be no storage of flow at the vertices. So in other words, the inflow of a vertex must be equal to the outflow. This rule does not apply to the source or the sink because they only have one way to go, don't they? So hopefully you're able to answer and fill in some of those ones there, because that goes with all of those there. Then I watched lesson 7094 of Flow Networks from Maths Online. And I found that it helped me quite a bit with question 1 and 2, because when I was looking at question 1 and 2, I was going, what? Don't really get it. Question 1 was a bit more obvious, but I think what you have to know is, in question 1 especially, if you've got 2 arrows coming in, one's a 5 and the other's a 5, that means that there's an allowance of 10, say, litres being allowed to go into that particular point. So that means that only 10 litres will be able to come out the other end. So that's why the other end, okay, they would probably only have 7 and 3. So I'm trying to remember. Consider the vertex for the flow diagram on the right, where the red edge is the flow and the black edge is the capacity. So calculate the inflow and the outflow. So red is the inflow I've written down on my sheet. So add the red numbers to work out the inflow. And then the outflow, add the red numbers out of the dot. So the red numbers out of the dot are 7 and 2, so that would equal 9. Saturated numbers are the numbers that are the same. So wherever the black and the red numbers are the same, that's where the edges are saturated. They can't take any more. Now question 2 got a little bit tricky for me. So what you have to know is when something's coming into an edge, a vertex, when something's coming into a vertex, sometimes you can split that amount evenly, and I found that one out from one of the Bodgers videos that I watched. So for example, the maximum flow in 2 was fairly obvious because it's a nice straight line. Smallest number is 100, but the maximum flow in 2B was a little bit harder. So I think what you're looking at there is you're looking for the maximum flow going into T. So when you're going into T, the sink, there's 100 from one direction and there's 100 from another direction. So because there's 100 from 2 directions, that adds up to 200. So that's what I assumed was the maximum flow there. And in C, you've got 200s coming out from the source. Then you've got a 90 and a 10 going from the E vertex. You've got 100 coming from the F, so there was lots of numbers happening there. So the only thing I could assume in the end was going from B to C, and then from F to C, you had a capacity of 290, going into that vertex C, but only 200 could go into T. So that's where my 200 had to be the maximum flow. You couldn't use the 190 and the 100 because 290 wouldn't fit down that final pipe 200. So that's why I think that is the maximum flow. So then it started talking about cuts. So a cut in a flow diagram is the selection of edges that when you remove them, it disconnects the source from the sink. So it's like you've got a busted pipe and you're stopping the flow from the source to the sink, if we're talking about water, okay? Flow networks work best with water, quite frankly. And a cut capacity is the sum of all the capacities of these included edges. So if you found this one a bit difficult, here's this one here. Now I don't like it when they do the circle bits because that kind of puts me off. I like it better when it's an actual just a line. So for this one here, example 10E2, find the capacity of the following cuts. That one's fairly straightforward. You're having a look to see where the red line goes across the edge, okay? So you don't really need to worry too much about that bit. You need to worry about where it cuts those 3 edges, okay? And if you follow, I'll do this one in purple. If you follow, that's the flow from the source to the sink. That's the flow from the source to the sink, and that's the flow. So you want to cut those purple flows. That's what a cut does. All right, so we cut it in 3 spots because there's basically 3 routes, isn't there, to get from the source to the sink. And if you cut it along a lovely line there, you've cut it at the 7 weighted edge, the 1 weighted edge, and the 6 weighted edge. So the capacity of the cut is the 7 plus the 1 plus the 6. Now this one over here, B, is it trickier? I'm not sure. Let's go over it. So they're cutting it here and they're cutting it here, okay? This one here, from what I understand, has already been cut. So if you followed the flow, it would flow naturally that way if you follow the arrows. So I'll just get rid of that now. So that's this one here we don't actually count. I know it does cut across it, but if you've already cut the water from S to E, there's no use cutting this pipe again. Does that make sense? This pipe's already been cut, so it's not going to flow here anyway. So that's why we don't include that one. So we only add the 100 and the 190, and that's where we get the 290 as the capacity of the cut. I hope that makes a bit more sense. So if you think about it in terms of water, hopefully it will make a bit more sense to you. All right, so then 10E2, is that it? Yep, okay, I'm up to 10E2 on my computer as well. So this one pretty much said the shorter and more common way to draw a cut is as a curve. I like these ones better. I'll leave it up to you which one you want to use, okay? So you need to know that a cut is a line or a curve that stops all of the flow from the source to the sink, okay? A minimum cut is a cut that has the smallest possible cut from the source to the sink. Obviously minimum. We hopefully all know what that means. All right, so let's have a look at example 10E. This one was a little bit harder. So first of all, it said find every possible cut. So here were mine. All right, they gave us 4. They gave us 1, 2, 3, 4 different possibilities. Possibility number 1, where did that go? Sorry about that. Possibility number 1 was this first cut over here. Okay, that was fairly straightforward because 1 and 2 are definitely going out from the source to the sink. Okay, so that was easy. Add 1 plus 2, that gave me 3. Now B is a crossways. Sorry, I've done it downways. Apologies for that. Now this one, you've got this coming out this way. This one's already been cut off, okay? And then this one here is coming that way. So that's why we only include that 2 and that 2. You don't include the 3 because the water flow's already been cut off by this first 2 down here, okay? So that's why that capacity is 4 only. Question C, we have got this one here, cut, right? We have got this flow here, cut there, and then we've got this flow here, cut there. So we've got 3 different routes to get to from the source to the sink, and if we cut those 3, then it's 1 plus 3 plus 1. So that's got a minimum cut of 5. And then the last one is fairly straightforward. They've cut the 2 edges at the end there. 2 plus 1 is 3. So the minimum cut out of all of those, we've got a 3, we've got a 4, we've got a 5, and we've got a 3. So the minimum cut is a 3. So I hope that makes sense. So watch out. If the flow seems to be cut. Now I watched the maximum flow minimum cut video from Maths Online. It actually made a lot of sense to me there. So if you are struggling, please watch those because they help me, so hopefully they'll help you as well. Now from the Maths Online, I found out that the minimum cut, if you can work that out and you got that one straight in your head, that will actually help you work out the maximum flow. So if you're finding maximum flow difficult, but you know how to do minimum cut, that kind of does it for you as well. All right, so then I had to go at question 3, just to make sure you guys were okay with those 2. So I'll just get that up on my computer. It says, what's the capacity of these cuts? All right, so 3A, the cuts were fairly straightforward. It was the 3, and the 2, because it definitely cut off the 3 routes of the flow. So that one was 8. That was pretty easy. B, now remember, you're cutting through the black line. You're not counting any other lines. So the red line went through the first route that went along the bottom, 1, and then the 5 along in the middle route, and then up at the 3 weighted edge up in the top route. So you had to add up the 3, the 5, and the 1 for that one to get 9. C says red line through 5 edges. It does go through 5 edges. However, the bottom one, I actually think this answer is 11, not 14. You can let me know if you don't agree, please. If you follow the bottom route, if you cut it off at the 1 edge, the water won't flow to the 2 and the 3 edge. So I don't quite understand why in the answer they've given the answer as 14, because there's not another route that will hit that 3 weighted edge. So anyway, I'll keep going. So if you follow the top route, it definitely cuts at the 4. So it's the 4 and the 1 so far. And then if you follow the cut to the 6, it definitely cuts through the 6, and that will cut off that root as well. So of the 3 roots, it cuts at the top root at 4, the middle root at 6, and the bottom root at 1. So I don't quite understand how they got 14. I actually get 11. So you just tell me if you think it's any different. And then D is fairly straightforward. It cuts through the 3, the 1, and the 6. So that one was obviously 10, and each of those roots were also cut from going from the sinks root to the source root. So hopefully that one made sense. Question 4, which edges are included by the cut? All right, again, you've got to keep in mind the root of the water flow, okay? So the first cut, AB, no, AB is actually going the wrong way, so we don't include that one. Also, if you kind of went backwards, AB was already cut off from flowing by the AC pipe being cut, okay, or blocked, whatever you want to call. So the AC edge is definitely included, and the AD edge, because that's going to stop the water flowing back to the sink as well. So that one, if you wanted to add it up, actually had a capacity of 14, according to me. For 4B, I said, again, it's flowing from A to D to get to the source. So I said yes for A to D. C to T, yes, it's flowing. So if you don't cut it off anywhere else, or if you go straight through that middle, C to T is definitely an edge that needs to be included. And the last one to include was B to C. Now, it's not been cut from A to C. It's been cut after that from C then to B. So we do actually include that B to C cut, even though I know it looks like it's not going to go to the sink. If you still went around, it will still finally end up at the sink if you didn't have any red lines on any of the roots. So you have to include the B and the C as well. All right. So when I added all of those ones up, if you're still working out capacity, because that is for question D, that capacity ended up being 16. And for 4C, if you follow that one, we include AC definitely, because that's a direct straight line to the sink. We include D to T because that's also a route to the sink, but I didn't include A to B because that's already been cut off by the A to C pipe being blocked. Okay, so when we add those two up, we only have to add up 4 and 7, and that gives me 11. Okay, so hopefully you're all right to there so far. All right, and the next one, what does the maximum flow minimum cut theorem state? So if you go to the next page in your textbook, give me a sec, it states pretty much what I just said already, that there's always going to be some flow and cut that have an equal capacity. So pretty much from Maths Online, your minimum cut is going to equal your maximum flow. Okay, and again, if you haven't watched that, I really suggest you do because it was good. All right, finding the minimum cut. All right, I haven't done these yet. I'm going to do those now. So I'm going to stop the video now and upload it and let you get on with this. Thanks.